Here we have to see what is Zigbee. The Zigbee is a network that it is a network that was released in 1990s. So what happens is that it's a protocol layer. Okay, what happens is it released a typical standard like RFC and Zigbee. There are still hundreds of companies which support this, even though it was released in the 1990s. And then there is an alliance group of companies. You're giving some basic information about Zigbee, and then the main thing comes over here. It starts from here. Zigbee solutions are aimed at smart objects and sensors that have low bandwidth and low power needs. So your main object, your smart objects with sensors that have low bandwidth and low power need, that's why you're using Zigbee. Okay, it should be see the data which is got by Zigbee Alliance should be interoperable. That is, it can perform many other operations, not just one. And then even though many different manufacturers have manufactured them. So the main areas where Zigbee is most well known is automation for commercial and retail home applications and smart energy. So in industrial and commercial automation spaces, Zigbee based devices can handle various functions like measuring temperature, humidity tracking and all. For home automation is also same thing, controlling lighting, thermostats and all can be measured by Zigbee. So you have Zigbee smart application layer which is being considered over here. So it smart energy brings in interoperability which can be controlled and monitored. So you have this your traditional high level Zigbee protocol stack. There you have your application support. Then you have network and security, MAC layer, physical layer. So you should know MAC layer, physical layer, network support. These are the four normal common ones. And then you have application support and then application or profiles. So in these two are your IEEE 801, 802.15.4, and then these two, your network and security layer and application support is your Big B, is your Zigbee platform stack, and then this Zigbee or vendor specific. So you have Zigbee network and security layer over here. What is its mechanism is to network it mechanisms for network startup, configuration, routing and securing communication. As the name suggests, it should set up network and then have configuration, routing and securing communications in place. So this must calculate routing paths and what is often changing technology topology. You can have star topology and then you have mesh topology, right? So if it should be able to match different types of topology also. So the network layer is responsible for appropriate topology, which is often can be tree or star or tree, as I said. And then instead of mesh, you should write tree. Okay, and then you have MAC layer where AES, that is advanced encryption standards, are maintained. So it is a 128-bit key. So this is also used to secure the layer. Okay, then what happens is you have Zigbee IP. So the next part is Zigbee IP. So what happens here is your normal Zigbee that is supported by IEEE, this continues, but with IP and TCP/UP protocols are also involved in this. So what happens is this and all happens, the IP and TCP/IP TCP or UDP is supported in network and transport layers. Okay, the Zigbee specific layers are now found only at the top of the stack for the application. Zigbee IP was created to embrace open standard. So it can not only, it doesn't only have to talk about your protocol stack for applications, but I mean not only IP, but it can also have 6 low WPAN and then RPL to provide which provide low bandwidth and low bandwidth, low power and cost effective communications. Zigbee IP is a critical part of so you're seeing that it's a critical part of smart energy. Okay. The version 2.0. So what happens here is you're not just limiting the case of IP, but you're using the standard based IoT stack that is normally utilized. So the standard based IoT stack is So it is as follows. That is, you have your Zigbee IP on your top. You have UDP and TCP. These are your new layers which have been included. IPv6, 6 low WPAN, ND, and then ICM, ICMP version 6, and then you have or RPL. So your 6 low pan adaptation layer, then you have your MAC layer of this IEEE technology, and then you have the same IEEE technology and 2006 version of physical layer. So what happens here is it supports 6 low pan as an adaptation layer. So what happens in the adaptation layer is that so you have mesh over route over a method which is being used for packet forwarding. You use packet forwarding, and then which is this is supported by ICM v6. All this whichever is written here, that is neighbor discovery. Like you're finding whoever is your neighbor and then checking. It allows you to forward packets like that. Both TCP and UTP are also supported as the connection, and then you have physical layer. The physical layer over here is you mainly have like we discussed before, it is mainly concerned the IEEE technology mainly is concerned with physical layer and math layer. So what happens is in the physical layer, that is your PHY. So in this it supports the extensive number of PHY options that range from you don't actually have to write that, you have to write which is based on direct sequence spread spectrum, that is your DSSS modulation. It's what is DSS modulation? It's a technique which is used to spread frequency domain. Okay, so you have channels with different data rates. So what you're doing is you're sending it through those. So you have 2.4 900 megahertz, then 915 megahertz, and then 868 megahertz. So in 868 megahertz, it's only one channel with data rate of 20. With 900 megahertz, it is 10 channels with data rate of 40 kbps. And then you have 2.4 gigahertz, that is your 16 channel with data rate of 250 kbps. So these are your original layer transmission options. Okay, then you have PHY also is introduced. The version 15 is also introduced with OQPHY. In this, the DSS, that is your direct sequence spread spectrum. What happens is this employs offset quadrant phase shift. So it checks over the phase shift modulation technique and uses a 4 unique bit value that signals the phase shift as an offset. An offset function during this allows us to transmit more reliably, saying that there is an offset and then you can't transfer the data. What happens in BSSK is you have a binary phase shift, quadrant phase shift, binary offset quadrant phase shift. That's why UOQPHY. Okay, that in your physical layer, or offset quadrant phase shift, and then you have binary phase shifting key modulation. This requires two unique phases shift as encoded in the encoded scheme, that is your zeros and ones. So here in last we have ASK, that is your this is a parallel sequence spread spectrum. So this is everything was BSS. That is your DSSS, that is your direct sequence spread spectrum. But in this, it is your parallel sequence spread spectrum. So you have amplitude shift keying. So what is this? Is amplitude shift keying and BPP and this plus BPSK modulation. So the advanced encoding scheme of this increases the range, throughput, data rates, and then signal integrity. So it makes its amplitude shift of the phase to different signals via bit values. we have the format for PHY. You have a preamble, you have a start frame delimiter, frame length, and then PHY service data layer. This contains the data, that is your 0 to 127 bytes, and then you have 6 bytes for preamble and start of frame delimiter, frame length. This is your PHY header. This is your synchronization header. So you have this is for your physical layer. Since you're writing all of this, that is your standardization layer, your physical layer, your Zigbee IP, and then your topologies, your security systems, and the other technologies, everything comes under 10 marks. You don't really have to write a lot of content. You can also skip content if you don't want to write it. So what happens in Mac layer is it manages the access to your physical channel by defining how devices in the same area will share, and it will allocate. Okay, so what it does is the Mac layer performs the following tasks. It performs as a network beaconing for devices acting as coordinators. Okay, so it'll become a new device to use the technologies. And then you have pan association and disassociation by a device. So it will maintain all your associations and disassociations, so that once it is out of the network, you don't give it access to connect. Then you have data security, reliable link communication between two Mac entities. So the Mac layer achieves these tasks by various things. That is your data frame, that is your handles all the transfer of data. Beacon frame, that is your it is used for transmission of beacons from PAN coordinators. Then you have acknowledgement frame that confirms a successful uh, reception of a frame. And then you have Mac command frame, that is it gives you the communication between the devices that with the given frame format shown. So this is your Mac frame. What happens here is you have a preamble, like in PHY format. You have a start frame delimiter and frame length, and then here you had physical PHY service data units, right? So here what happens is it splits. Now you are giving a Mac layer view. So in this is the Mac layer. So here you have a Mac header, Mac payload, and then Mac footer. So header, footer, and then payload. In the header section, you have frame control, sequence number, destination pan identification, and then you have destination address, source pan identification, source address, and then you have frame payload. Mac payload is frame, you get the frame payload, and then you have Mac footer, that is your frame check. So it is like so much data has been sent. So you're giving a checking range for it. Here, what you're doing is um, in your first header field, it composed of you just write down whatever is there. That is your frame control sequence number. It gives how many, it is like 1 2 3 you need to follow, or 1 5 4 3 sequence number. Destination pan, destination address. Okay, this destination pan, what is your final now if you are sending it to somebody else's phone who lives in a different house, so they have a different personal area network, right? So you're giving their pan identifier, and then you're giving their destination address, that is your friend's phone. And then you have your source pan identifier, that is your house network connection, and then you're giving the source address, that is your phone address. So this is what happens over here. These four are your addressing fields, and these two are your just under Mac header. Then you have topologies that needs to be checked, that is star, peer-to-peer or mesh topologies. Mesh networks are tied together by many nodes. So this allows the communications to directly happen through transfer of communication. So you have this as your topology. So you have PAN coordinators, and you have fully functional devices which are present. So PAN over here coordinates with your fully functional devices, which in turn coordinates with your reduced function devices. So next we go on to security. So in security, what happens is you're using advanced encryption standards. So you don't want the data to go as it is. So you're encrypting the data using the advanced encryption standards. what is AES is a cipher block. That means that it operates on fixed block values. It doesn't just take every word and then um, you don't encrypt it. So what you're doing is you're putting it in the category, and then you're converting the whole block. So you're using popular algorithms, and then symmetric key cryptography. That is, you'll have one key, and your the same key which you're using will be given to both encryption and decryption ends. And then from there you can encrypt and decrypt by using the same key values which are being present. So over here what happens is security is enabled in the MAC header. Then you have auxiliary security header field which is added to the MAC frame. So in this field, the bit is set to 1 for security. Once the bit is set, the field is called auxiliary security header, that is created after source addressing field. Finally, we have our competitive technologies. That is your see, we have different this thing, that is your iOS 18007 standard, which is proposed for industrial and commercial IEEE 802.15.54, which is more generic, and this can be used in active radio frequencies. And dash 7 by which is used by US military. So dash 7 technology offers low power consumption and compact protocol stack up. So this is better, but it is used mainly in military or army bases. So this is our wireless sensor. So dash 7 is the one which is used over there. Other than that, you have one more thing, that is your iOS 18,000. So you have a topic called LoRaWAN, that is your low power wide area network, which is no, which is known as low power wide area network. That is LPWA. That has low power battery ends that and long range batteries that are used. So what it is you can use it for business opportunities and all. So you don't have to use a lot of power. So your standardization and alliance will be you have your was a physical layer or layer 1 modulation. So it is mainly a layer 1 modulation, and then you have a LoRa, that is your Semtech LoRa as a layer 1 modification. So what it is so it is a LoRa alliance. Okay, so what you're doing is you're giving a broader scope and creation of LoRa alliance through a company called Semtech. Okay, so what happens here is you make it as LoRa, and then it becomes LoRa and WAN. So you're using via low power wide area network. Here what happens is that your physical layer is handled by Semtech, and then while LoRa alliances handle the MAC layer. So what happens here is LoRa alliances, that is your 868 or 915 megahertz or other regional bands. Okay, and then your Semtech, that is your LoRa physical modulation. Then LoRa alliance is your LoRa WAN MAC layer. Okay, and then you have CoAP, MQTT, IPv6, RAW, or others, and then you have applications on top of it. So your physical layer, what happens is that you have a variety of LoRa alliances which are giving you different frequencies with which you can connect to in parallel. So you have regional bandwidths which have been given to you. So here the data varies on the frequency band. The data varies on the frequency band and the adaptive data rate. Okay. The algorithm, it is like an algorithm which manages radio signals for each endpoint, and then these endpoints are close to the gateways. Then you have a spreading factor which archives less distance and communication but transmits it faster and resulting in less airtime. You have a MAC layer. What happens here is that The LoRaWAN specification takes advantage of LoRa physical layer, and then the endpoints. Okay, so you have so for the MAC layer, what happens is you have mainly three classes: class A, class B, class C. Under class A, that it is default implementation optimized to battery powered nodes, which are bidirectional communications. So you can receive two-way transmissions. And then this class B is for experimental data, that is LoRaWAN 1.1. So this is predefined. This is predefined. Class B should get an additional receiving window. Then you have class C that adapts for powered nodes. So this is this keeps listening in the receiving window when the transmissions is not happening. So the LoRaWAN message is either uplink or downlink, which is composed. So in this you have a MAC header, MAC payload, and message integration in your MAC layer. Uh, so what happens is the main things you need to see here is LoRaWAN endpoints are uniquely addressable through the following. So it can have a end device ID, and then the endpoint can have a global application ID, that is, or a app EUI. And then you have a LoRaWAN network endpoints, which are also known by their end device addresses, known as dev ADDR. That is your 32-bit dev address. So what happens here is you have your network identification, that is your network identification address, that is your NWK endpoints. So you have topology, that is it's the star of stars topology, as they told, and then the gateways are connected to the back network using standard connections of the endpoint from one gateway or more. So what happens here is that app data is sent, and then your it goes through your radio PHY, and then it goes to your LoRaWAN MAC address, IP tunnel, and then IP transport app data. So you have a backhaul, you have an API, you have roaming LoRaWAN, and then you have different data which goes through it. So you have physical layer frequency bands which are sent on physical layer. The application is contained in upper protocol layers. These upper layers could just be raw data on top of MAC layers. So what happens here is you have LoRaWAN manager, that is your radio frequency. So you're sending it, app data is being sent by radio frequency to LoRaWAN radio physical layer. So from there it takes it to the MAC address layer, and then IP tunnel happens, and then IP transport happens. Tunneling, while going to the IP tunnel, it is called gateways. From IP tunnel, while transporting, it's called network servers, and then application servers. Then you have security, that is you have different components of the architecture that has endpoints and must be implemented in two-layer security. So you have two-layer security, that is your first layer is called network security. So you have network encryption, and then app encryption, and then data. So your network encryption, what happens here is the MAC layer guarantees that the authentication by endpoints. So it takes from the endpoint, and then before sending it through the LoRaWAN network server, what happens is it is encrypted. The data gets encrypted from end to end. Then what happens is it's encryption is performed by AES, and then the network as key. So you use the network server key and then ensure that the integration is maintained by checking MIC of every data message that is encrypted. The second layer happens when app is key, so which performs encryption and decryption function between endpoints. So further, what happens is, so you from encryption, you have the encrypted data, right? So this encryption so it makes sure that the application doesn't have any payload access to it. And then you have app key. So if you see this diagram, it states that the first encrypted data, first you put the encrypted data into network encryption. Okay, so what you do is you have a separate network encryption which is happening. So first it's encrypted, then you're putting the encrypted data and again encrypting it, and then the device sends the packet in 3. Okay, so the device goes in 3, LoRaWAN device, and then it goes to 4. That is your uh, APs, that is in range of the receiver packet. So this gets the packet and then sends it to network server decryptor. Okay, so this network server decryptor decrypts the network and then it's forwarded to your AS decryption. So AS decryption happens, and then that is here your app server decryption happens, and then your network server selects the best AP for returning format.